All right, in this video, we're going to be talking about frequency distributions. That's section 2.1. And in this section, we're going to be developing an ability to summarize data in the format of a frequency distribution and a relative frequency distribution. And in a frequency distribution, we're going to identify values of class width, class midpoints, class limits, and class boundaries. Okay, so when we work with large data sets, a frequency distribution or a frequency table is often helpful in organizing and summarizing data. A frequency distribution does help us understand the nature of the distribution of a data set. Here, that can tell us whether or not we have what we call a normal distribution or a non-normal distribution. We'll talk about normal distribution later in this course. Okay, so let's define what a frequency distribution is, or a frequency table. It shows how data are partitioned among several categories or classes by listing the categories along with the number or frequency of data values in each of them. So in this case, let's consider this frequency distribution that we have here. Okay, so here we're going to consider the IQ scores of the low level or the low lead group listed below. Okay, so here this frequency distribution that you see on the left, it does summarize those IQ scores. And the frequency is, or for a particular class, the frequency is going to be the number of original values that fall into that class. Okay, so here's what a frequency distribution looks like. On the left, you see the IQ score in a particular class. So these numbers that you see here from 50 to 69, that represents a class. Then 70 to 89 represents a class, and so on. So these are your classes that are on the left side of the frequency table. And of course, these numbers represent the frequency. That's how many data values that fall within each of those particular classes. So like for 50 to 69, the two data values that are within that class for the IQ score. For 70 to 89, 33 is the number of data values that fall between 70 and 89, including those two, 70 and 89, and so on. Okay, so in a frequency table or frequency distribution, here we can identify important things here. Okay, so here the following standard terms are sometimes used in constructing frequency distribution and graphs. One of them is the lower class limit. Well, your lower class limits are going to be the smallest number that can belong to the different classes. So if you look at this table, the 50, 70, 90, 110, and 130, those are your lower class limits. We also have upper class limits. Those are the largest numbers that can belong in those different classes. So here, these are your upper classes here: 69, 89, 109, 129, and 149. Okay. And then next is the class boundaries. The class boundaries are the numbers used to separate the classes, but without gaps created by the class limits. Now, the way they get the class limits is this. They subtract 0.5 from each of the lower class limits and add 0.5 to each of the upper class limits. So in this case here, for the 50, if I subtract 1/2 or 0.5 from 50, I'm going to get 49.5. And I'll do the same here for these other lower class limits. 70 minus 0.5 will be 69.5. And then 90 minus 0.5 will be 89.5. And then 110 minus 0.5 would be 109.5. And then 130 minus 0.5 would be 129.5. And for the upper class limits, I'm going to add 0.5 to each of these upper class limits. So here's 69 plus 0.5 will be 69.5. 89 plus 0.5 will be 89.5. 109 plus 0.5 would be 109.5. And then 129 plus 0.5 would be 129.5. And then 149 plus 0.5 would be 149.5. So these are all of my class boundaries here. Okay. And some of these class boundaries do repeat, like the 69.5, 89.5, 109.5, and 129.5. Okay. So all your class boundaries are going to be 49.5, 69.5, 89.5, 109.5, 129.5, and 149.5. And also in a frequency distribution, we can also use what they call class midpoints. Now, the class midpoints are going to be the values in the middle of the classes. So in this case here, to find the class midpoints, you just take the sum of your lower class limit and the upper class limit and divide by 2. So like for 50 to 69, I'm going to take the 50 plus 60 plus 69 and divide by 2. That would give me 119. And if I divide that by 2, that will give me, what's it, 59.5. So the class midpoint for this first class would be 59.5. Now, for 70 to 89, we do 70 plus 89, divide that by 2, you'll get 79.5. And then you'll do the same here. You'll get 99.5 for this third class, 119.5 for the fourth class, and then for this final class here, that class midpoint will be 139.5. So each class midpoint is computed by adding the lower class limit to the upper class limit and dividing that sum by 2. And then finally, you have a class width. That's going to be the difference between the two consecutive lower class limits, or it could be two consecutive lower class boundaries in a frequency distribution. So in this case, if I do 50 from 70, these are two consecutive lower class limits here. So 70 minus 50, that would give me 20. So the class width for this frequency distribution would be 20. Okay. So now let's look at this first example that we have here. In this case, you want to identify the lower class limits, upper class limits, class width, class midpoints, and class boundaries for the given frequency distribution. Also identify the number of individuals included in the summary. So in this case here, if you look at the right, here's our frequency distribution here dealing with the age when the award was won, and that's in years, by the way, and their frequency. So we're going to identify these things here in example number 1. We'll start with the lower class limit. Well, lower class limits, I should say. So in this case here, the numbers on the left for each of these classes that you see here, those are your lower class limits here. So we just list those. That's going to be, in this case, 10, and then 15, and then 20, 25, 30, then 35, and then 40. Those are your lower class limits. And next, we're going to identify the upper class limits. Okay, so the numbers that you see on the far right are your upper class limits here. So we start off with a 14, and then 19, and then 24, 29, 34, 39, and finally 44. Those are your upper class limits. Next, they want the class width. Now, the class width is going to be the difference between two consecutive lower class limits. So let's start with these two consecutive lower class limits, 10 and then 15. The difference between those two, if I subtract 15 minus 10, that would give me 5. So the class width for this frequency distribution would be 5. Now, not only could I do the difference between any two consecutive lower class limits, I can also do the difference between any two consecutive upper class limits as well. Like 14 and 19 are two consecutive upper class limits. So if I do 19 minus 14, that would also give me the class width of 5. And then class midpoints. Class midpoints. So now to find the class midpoints for each of these classes, let's start up with from 10 to 14. I'm going to do this off to the side. That's going to be the sum of the lower class limit, which is 10, and the upper class limit, which is 14. That sum will be divided by 2. So if I do 10 plus 14, that's 24. And if I do 24 divided by 2, that would give me 12. So one of my class midpoints would be 12. Now, I could keep adding the sum of the lower class limit and the upper class limit of the second one and divide that by 2. However, I do know what my class width is. That's going to be 5. So that means if I want to find the class midpoints for the other classes, let's do this. Quick way of doing that would be to add 5 each time. So if I add 5 to that 12, the next class midpoint for this second class will be 17. Add another 5, that would be 22. That represents the class midpoint for 20 to 24. Add another 5, that would be 27. That represents the class midpoint for 25 to 29. And then add another 5, that would be 32. That would represent the class midpoint for 30 to 34. And then add another 5, that would be 37. That's the class midpoint for 35 to 39. And then for 40 to 44, add another 5 to that 37, that would be 42. So here I have 7 classes. I must have 7 class midpoints. Okay. Now for the class boundaries. Now this is where I subtract 0.5 from each of these lower class limits and add 0.5 to each of these upper class limits. Okay. So in this case, for the 10, if I subtract 0.5 from 10, that's going to be 9.5. Okay, I'm doing this on another color so that way you could see what my class boundaries are going to be. And then if I do 15 minus 0.5, that will be 14.5. 20 minus 0.5 will be 19.5. 25 minus 0.5 will be 24.5. 30 minus 0.5 will be 29.5. 35 minus 0.5 will be 34.5. And then finally, 40 minus 0.5 will be 39.5. Now, for my upper class limits, I add 0.5 here. So 14 plus 0.5 will be 14.5. And then 19 plus 0.5 will be 19.5. 24 plus 0.5 will be 24.5. 29 plus 0.5 will be 29.5. And then 34 plus 0.5 will be 34.5. Then 39 plus 0.5 will be 39.5. And then finally, 44 plus 0.5 will be 44.5. Now, some of these class boundaries do repeat, but you do write them only once. So all of my class boundaries will be 9.5, and then 14.5, and then 19.5, and then 24.5, and then 29.5, 34.5, and then 39.5, and then finally the 44.5. Okay, so you can pretty much see the 14.5, 19.5, and so on, they do repeat. So these are all the class boundaries. Then they tell us to identify the number of individuals included in the summary. So what they're looking for is the total frequency. That means I need to add each of these individual frequencies for each of those individual classes. So that means I need to add 31 to 34 to 16 to 2 to 6 plus 2 plus 1. And if we add those numbers together, you'll end up with 92. So 92 represents the total frequency, or the number of individuals that is included in this summary that we see here. Okay. So that's how we identify the bits and pieces that are in a frequency distribution. The lower class limits, the upper class limits, the class width, the midpoints, class boundaries, and the total frequency in that summary. Okay, now next is the procedure for constructing a frequency distribution. Okay, so this right here is the procedure for constructing a frequency distribution. Here we construct a frequency distribution so that we can summarize large data sets, so that we can analyze the data to see the distribution and identify outliers, and so that we have the basis for constructing graphs, such as histograms, which we'll talk about in the next video. Okay, so these are the steps for constructing a frequency distribution. Number one, you want to select the number of classes, and it will usually be between 5 and 20. Now, in some of these examples, you will be told the number of classes that you will need to use. And then the number of classes might be affected by the convenience of using round numbers. And then number two, you're going to calculate the class width. To find the class width, you take the maximum data value in that data set minus the minimum data value in that data set. That difference will be divided by the number of classes that they give you. Okay, and it's usually best to round up. And it's also best to round that value to get a convenient number. So it's best to round up. Number 3, choose the value for the first lower class limit by using either the minimum value or a convenient value below the minimum. Then number 4, you're going to use the first lower class limit and the class width. Using the first lower class limit and the class width, you're going to list the other lower class limits. So that means you're going to add the class width to the first lower class limit to get the second lower class limit. And you'll keep adding the class width to get the second lower class limit, to get the third, and so on. You just follow that pattern. Then you're going to list the lower class limits in the vertical column and then determine and enter the upper class limits. Then finally, you'll take each individual data value and put a tally mark in the appropriate class. And then you're going to add those tally marks to find the total frequency for each class. And then that's your procedure. Now, when you construct a frequency distribution, be sure that the classes do not overlap. Each of the original values must belong to exactly one class. Include all classes, even those with a frequency of 0. Okay. Now, let's look at the second example of constructing a frequency distribution. The data represents the body mass index or BMI values for 20 females. Construct a frequency distribution beginning with a lower class limit of 15 and use a class width of 6.0. So already they're giving you the class width of 6.0. The problem is we need to know how many classes that we're going to need for this frequency distribution. Now, what I'm going to do here is give you a way of calculating the number of classes that you need. Okay, so let me start off by doing this. The number of classes that you will need, that's going to be equal to this. Number of classes is going to be this. I will take the maximum value, and I'm just going to abbreviate this as max value, minus the minimum value. I'll abbreviate this as min value. And that difference will be divided by the class width. Okay, so in this case here, we need to look at this data set carefully and find out what the maximum value is. In this case, I see the maximum value is 44.9. So I'm going to take 44.9, subtract from it the minimum value. Well, the minimum I'm seeing is 17.7. And that will be divided by the class width that's given to you, that's 6.0. Okay, so if I do 44.9 minus 17.7, I'm going to get 27.2. 27.2 divided by 6.0. This is what I come up with as a repeating decimal, 4.53, and the 3 repeats. Okay. Since I came up with a decimal, I'm going to round this up to the next whole number. So 4.53 repeating, rounded up would be 5. So the number of classes that I'm going to have in this frequency distribution would be 5. Okay. All right, so now I'm going to go ahead and do my frequency table or frequency distribution. Okay, so my frequency table is going to look like this. All right, the left column would be the body mass index, which is, of course, BMI. The second column is the frequency. Now, of course, the lower class limit, I'm starting off as 15.0 as given in the problem. So we'll start with 15.0. Now to come up with my next lower class limits, since the class width is 6.0, I'll just add 6.0 to the 15 to get the next lower class limit. So 15 plus 6 is 21.0. And then the next one, add 6 to the 21, you'll get 27.0. Add 6 to that 27.0, you'll get 33.0. And then finally, since I'm only using 5 classes, that last lower class limit, I'll add 6 to that, will be 39.0. Okay, so now we need our upper class limits. Now to get that first upper class limit, I need to look at my data set. The data values that I have here are to 1 decimal place. So my upper class limits has to be to 1 decimal place. So to get that upper class limit, I'm going to take this 21, which is the next lower class limit, and subtract 0.1 from it. So if I do 21.0 minus 0.1, this is what I'm going to come up with, 20.9. Okay, all I did here was just subtract a 0.1 from this second lower class limit of 21 to get the 20.9. And I know my class width is going to be 6. So we'll add 6 to this 20.9 and keep adding 6 until I get all of my upper class limits indicated. So 20.9 plus 6 will be 26.9. And then 26.9 plus another 6 will be 32.9. And then 32.9 plus 6 will be 38.9. And then finally, 38.9 plus 6 will be 44.9. Okay, so I'm done with the left column. Now, I'm going to use my data set to come up with my frequencies here. So that means the first class is from 15.0 to 20.9. I need to find or count how many data values that I have that fall from this data set that fall between 15.0 and 20.9. And it does include these endpoints here. So if we look at this, I see the 17.7 falls within 15.0 and 20.9. Also 19.2 falls between 15.0 and 20.9. And 18.3 falls between 15.0 and 20.9. And that's it. So that means that there are only 3 data values that are between 15 and 20.9. So that frequency for that class will be 3. And now for 21 to 26.9, I need to count the number of data values that are between 21 and 26.9. And that does include those endpoints here. So let's see here. Well, here's one data value right here, 21.6. And another one, 26.6. 25.8 falls within those two. Let's see, 25.4. And I'm missing one right here, that 24.6. Let's see, that 26.1, 24.4, 21.1, and 25.8. So if I count this up, that's 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 data values that fall between 21.0 and 26.9. So that frequency for the second class is 9. And then 27 to 32.9. Let's see, I'm going to use a different color here. I need to find data values that are between 27 and 32.9. Well, I see 1, 2, yeah, that 31.4, that's 3. 27.2, that's 4. And 32.4. That's a total of 5 that are between 27 and 32.9. So for 27 to 32.9, the frequency for that class will be 5. And then next from 33.0 to 38.9, I need to count data values that are between 33 and 38.9. Let's see, here's one, 33.5, that's 1, and 37.7. So there are only 2 data values that are between 33.0 and 38.9. And finally, for 39.0 to 44.9, well, there's only one, and that's, of course, 44.9. So that frequency there is 1. Now, there are 20 data values in this set. So if you add 3 and 9, that's 12, plus 5, that's 17, plus 2 is 19, plus 1 is 20. Okay, so this total frequency has to be the same as the number of data values that you have. Otherwise, you made a mistake. Okay. All right, here's another example of a frequency distribution. It says here, refer to the accompanying data set and use the 25 home voltage measurements to construct a frequency distribution with 5 classes. So you're told to use 5 classes here. Begin with a lower class limit of 125.6 and use a class width of 0.2 volts. Does the result appear to have a normal distribution? Why or why not? Okay, so here's our data set here that we have. Okay, so let's go and do our frequency distribution or frequency table, because that's what we're constructing, a table. Okay. Okay. Now this is in volts, and then our frequency will be the second column. All right, now we're told to do something here. Begin with the lower class limit of 125.6. And use a class width of 0.2 volts. And also we're to use 5 classes here. So if we're starting with 125.6, then the next lower class limit for the next class, I'll add 0.2 to that. That'll give me 125.8. And then add 0.2 to 125.8 to get the next lower class limit of 126. And then add 0.2 to the 126 to get the next lower class limit of 126.2. And then finally, our fifth class will have the lower class limit. If I add 0.2 to it, that'd be 126.4. And then we're going to find our upper class limits. Okay, our data values are to only one decimal place. So that means I need to subtract 0.1 from the next lower class limit. Here, this is 125.6. The next one is 125.8. If I subtract 0.1 from that 125.8, I will get 125.7. And then to get my next upper class limits, I'll add 0.2 to it because the class width for this is 0.2. So if I add 0.2 to the 125.7, I'll get 125.9. Add 0.2 to the 125.9, that will be 126.1. Add 0.2 to the 126.1, that'll be 126.3. And then finally, add 0.2 to the 126.3, you'll get 126.5. Okay. So those are upper and lower class limits for those 5 classes. Now for each class, we need to count the frequency. So that means between 125 and 125.6 and 125.7, we need to count up how many are within those two. And that does include the endpoints of 125.6 and 125.7. Okay. If we look at this, I see this one, 125.6. And I think that is it. So that means that there's only one data value that is between 125.6 and 125.7. Now for the 125.8 and 125.9, let's count how many data values are between those two. And it does include those two endpoints, by the way. Well, here's a 125.8. Another 125.8. Oh, I'm sorry. We don't include those. I mean 125.6. So let me do a different color. Oh, I'm right. Okay. I apologize. 125.8 and 125.9. There's one here. Another 125.8 here. And then 125.9 there. And there's another 125.8 that I skipped. So there are actually 6 data values that fall between 125.8 and 125.9. That frequency there is 6. And now for 126.0 and 126.1. Okay, let's see. Looking at this 126.0, there is one. There's a 126.1. There's a 126. Another 126. Another 126. A 126.1. Another 126.1. 126 is here. Here's another 126.1. 126.1. And 126. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 data values that are between 126.0 and 126.1. And now for the 126.2 and 126.3. In this case, if I use that data set, I do see a 126.2 right here and a 126.3 here another 126.3, another 126.3, okay, 126.2 is way up there. So in this case here, there are 5 data values that are between 126.2 and 126.3. And then finally, 126.4 to 126.5. Okay. All right, in this case here, 126.4 is right here. There's one. And 126.4 right here. There are only 2. So for 126.4 to 126.5, there are 2 data values. Okay. So this is what your frequency table looks like. Now, the other part of the question is, does the result appear to have a normal distribution? Why or why not? And what we mean by a normal distribution is this. The data values start small, increase to a high number, and then it starts decreasing to low numbers. If you were to look at this frequency distribution, you'll see that it does follow a normal distribution. So the answer to that question would be yes, because the frequencies start low, reach a maximum, and then become low again. And also, the frequencies are roughly symmetric about the maximum frequency, which is in this case 11. Okay. Okay. So this is the maximum frequency of 11. It's pretty much symmetric on the left and on the right. Okay. All right, the next distribution we'll talk about is a relative frequency distribution. A relative frequency distribution or a percentage frequency distribution is a variation of the basic frequency distribution in which each class frequency is replaced by a relative frequency or proportion or a percentage. Relative frequencies and percentages are calculated as follows. Here, the relative frequency for a class will be the frequency for that class divided by the sum of all frequencies. Okay, so that's usually going to be a decimal. But for a percentage for each class, you'll do the frequency for a class divided by the sum of all your frequencies, but you're going to multiply by 100%. Okay, that's the difference there between a relative frequency and a percentage. So for the IQ scores of low lead group, here we do a relative frequency like this one. Okay, here we got the frequency of each one of those classes. Now to find the relative frequency, you'll take each individual frequency for that class and divide that by the total number of frequencies here, and then multiply by 100. So the total frequencies for this one would be 78. That means for 50 to 69, I do 2 divided by 78. And then times 100%. Now here they give the answer to one decimal place. So that relative frequency there will be 2.6%. And then for 70 to 89, the frequency is 33, so I do 33 divided by 78 times 100. That gives you 43%, 42.3% to one decimal place, and so on. So the sum of the percentages in a relative frequency distribution must be very close to 100%. Now, there might be a small discrepancy, and that's permissible because of rounding errors, such as probably 99% or 101%. That's acceptable because of rounding. Okay, now in example 4, in example 4, here we're going to do a relative frequency distribution. And it says here, construct one table that includes relative frequencies based on the frequency distributions shown below. Then compare the amounts of tar in non-filtered and filtered cigarettes. Do the cigarette filters appear to be effective? And they do give you a hint that the filters reduce the amount of tar ingested by the smoker. Okay. So this is our table right here. And we're going to do a relative frequency. So let's do this. I'm probably going to do 3 columns here. Okay. The first column will be for tar, and that's going to be in milligrams. Okay. The middle column is going to be the relative frequency. This one will be for non-filtered cigarettes. And then another relative frequency column for the filtered. Okay. Now, let's look at this here. We're going to do a combined relative frequency table. And I'm going to start with the low numbers for the tar in filtered cigarettes. 5 to 8, and then 9 to 12, 13 to 16, and 17 to 20. Now notice for the non-filtered cigarettes, I already got the 13 to 16 and 17 to 20. So I'll pick up with this with 21 to 24, and then 25 to 28, and then finally 29 to 32. Okay. So let's start up with the relative frequency for the non-filtered cigarettes. Okay. As you can see here, there are no frequencies for 5 to 8, 9 to 12, and 13 to 16. So those are automatically going to be 0% for 5 to 8, 0% for 9 to 12, 0% for 13 to 16. Okay. Now, for 13 to 16, notice for the non-filtered 13 to 16, there's only 1. But we want the relative frequency. It has to be a percent. So in this case, we'll take that frequency of 1 And by the way, we need to count how many, the total frequency here. If I add 1 and 14, that's 15, plus 7 is 22, plus 3 is 25. And then for the filtered category, 1 plus 2 is 3, plus 6 is 9, 9 plus 16 is also 25. Okay, because I had to take each frequency, divide that by the total number of frequencies, the total frequency, multiplied by 100%. So for 13 to 16 in the non-filtered category, it's only a 1. So it'd be 1 divided by 25 times 100. That would give me 4, and that has to be 4%. So in the 13 to 16%, that's 4%. Okay. 5 and 8, 9 to 12 only have 0%. So this is just 4%. Okay. All right, so let me correct that. For 13 to 16, it's 4%. Now for 17 to 20, that frequency is 0. So that's automatically going to be 0% here. For 21 to 24, that's 14. So here, I'm going to do 14 divided by 25 times 100. And that would give me 56%. So for 21 to 24, 56%. And now for 25 to 28, there's 7. So 7 divided by 25 times 100 would be 28%. And then finally for the 29 to 32, there's 3. A frequency of 3. So 3 divided by 25 times 100 would be 12%. Okay, so I'm done with that category of non-filtered cigarettes in the relative frequency. And now for the filtered category. Okay, for 5 to 8, there's only 1. So I already know what that percentage is going to be. That's 1 divided by 25 times 100. That's 4%. Because that's the same as the 13 to 16 category or class. For 9 to 12, there's only 2. So now you're going to have 2 divided by 25 times 100. That would be 8%. And then for 13 to 16, that's 6. So 6 divided by 25 times 100. That's 24%. And then for the 17 to 20, there's 16. 16 divided by 25 times 100. That'd be 64%. Okay. And that's as high as the filtered category goes. It goes no higher than 20. So for the remaining classes, 21 to 24, that's 0%. 25 to 28, also 0%. 29 to 32, also 0%. So this is my complete and combined relative frequency for the non-filtered cigarettes and for the filtered cigarettes. Now, the question that they ask for is this: we want to compare those two and ask ourselves, do the filtered cigarettes appear to be effective? Okay. And the answer, of course, would be yes. Okay. And the reason for that is this: it's because the relative frequency of the higher of the higher tar classes is greater than is greater for non-filtered cigarettes. Because if you look at the filtered cigarettes, the tar, the relative frequency for those non-filtered cigarettes, the tar amount in milligrams is no higher than 20, where in the non-filtered is high. The highest is at 32. Okay. Okay, here's another example of a relative frequency distribution. In this case here, among fatal plane crashes that occur during the past 55 years, 650 were due to pilot error, 95 were due to other human error, 653 were due to weather, 617 were due to mechanical problems, and 619 were due to sabotage. Construct the relative frequency distribution. What is the most serious threat to aviation safety, and can anything be done about it? Okay, so let's start off with that frequency, relative frequency distribution. Okay. Okay, so on the left column will be the cause of that plane crash, and then your relative frequency. Now, before I do this, let's find the total frequency here for each of those categories, and I'll list the categories right now. Let's see, pilot error is the first, and then other human error is next, and then weather, and then mechanical problems, and finally sabotage. Okay, now let's find the sum of each one of these. The 650, and then 95, 653, 617, and 619. If I add those together, I'll get 2,634. That will be the total frequency for this frequency distribution here. Okay, the relative frequency will be given as a percent. And in that problem for pilot error, there was 650. So if I take 650, divide that by the total of 2,634 times 100. And I will get a decimal like this, 24.67729689. However, we're going to round to one decimal place here. So this amount as a percent will be 24.7%. So 24.7% of the fatal plane crashes were from pilot error. Now, for other human error, there was 95 from other human error. So I take 95 divide that by 2,634 times 100. And to one decimal place, this will be 33.6%. Keep in mind, we're rounding to one decimal place. And then for the weather, there were 653 plane crashes that were due to weather. So 653 divided by 2634 times 100. That's going to be 24.8% rounded to one decimal place. And for mechanical problems, there were 617 crashes that were due to mechanical problems. So 617 divided by 2634 times 100. This will be approximately 23.4%. And finally, for sabotage, there were 619 crashes that were due to sabotage. So 619 divided by 2634 times 100 to one decimal place, that's approximately 23.5%. Okay, so that's my relative frequency table. All right, now the next question that they asked was, what is the most serious threat to aviation society and can anything be done about it? Okay, aviation safety. Well, by looking at this, they're saying that weather, that's 24.8% of the crashes are due to weather. So pretty much weather is the most serious threat to aviation safety. So I'll just write this out. Weather is the most serious threat to aviation safety and what can be done about it. Now, in the homework, they're going to give you a choice of answers, and then you'll have to choose the one that is going to be appropriate for that. Okay. So in this case, weather monitoring systems can be improved. Okay. So that's how we create a relative frequency distribution for this particular situation. Okay, next we'll look at a cumulative frequency distribution. Now, cumulative frequency distribution is another variation of a frequency distribution where the frequency in each class is the sum of the frequencies for that class in all previous classes. Okay, so we take that frequency distribution for the IQ score of low lead groups here. You'll see the IQ score and the frequency. Now, what they do for the cumulative frequency, they're using the original frequencies of 2, 3, 35, 7, and 1. We add 2 to the 33 to get the second cumulative frequency of 35. This 2 plus that 33 gives you the 35. This 2, we just bring that over. 2 plus the 33 would give you 35. And then add 35 to the next frequency of the next class. 35 plus 35, that's 70. And then 70 plus 7 is 77. And then finally, 77 plus 1 will give you 78. Okay. So it's just pretty much the frequency in each class is going to be the sum of the frequencies for that class and all previous classes. So in example 6 here in this video, if I can get to it, here we go. We're going to construct a cumulative frequency distribution for the given data. And this deals with the age in years of Best Actress when the award was won and their frequencies. Okay. I'm going to draw this down at the bottom. So in this case, here's the age, and this is the frequency. And the age, of course, is going to be in years. Now, the way I'm going to write my classes, instead of doing the 20 to 29, I'm going to use the phrase less than. And it's going to be less than the next lower class limit. The first one is 20 to 29. The next lower class limit is going to be 30. So that first class will be less than 30, which is the same as saying 20 to 29. And then the next class will be less than. Well, let's look at this class width. Between 20 and 30, that difference is 10. So in this case, if I add 10 to the 30, that's going to be 40. That's less than 40 for this 30 to 39. And then next will be less than. 40 plus 10 would be 50. The next one, less than. 10 plus 50, that's 60. The next one, less than. 10 plus is 60, that's 70. And then less than. 10 plus 70, that's 80. And then finally, less than. 10 plus 80, that'd be 90. Okay. So now let's fill in our frequencies here, or the cumulative frequency, as I should say. So less than 30, that's a 20 to 29 category or class. That's 27. So that 27 goes here. For less than 40, well, that's 33. And then we had to add that to the 27. So 33 plus 27 would give us 60. And then less than 50, that's going to be these three classes right here, the 12, the 33, and the 27 added together. That would give us 72. And then less than 60, that's going to be these four classes here. 2 plus 12 plus 33 plus 27, that's going to be 74. And then for the less than 70, that's going to be these five right here. So I had to add these five frequencies here. 4 plus 2 plus 12 plus 33 plus 27. That would be 78. And then less than 80, that's these first. That's all of these with the exception of the last one. So it'd be 1 plus 4 plus 2 plus 12 plus 33 plus 27. That's 79. And then finally, less than 90, that's the sum of all of these frequencies, which will be 80. So that's how we construct a cumulative frequency distribution. Okay. All right, next we'll look at normal distribution. And one of the examples they did ask, does the frequency distribution appear to be a normal distribution? Well, here's how we determine whether we have a normal distribution here. Okay. Now, frequency distribution can help us understand the distribution of the data set, which is the nature or the shape of the spread of the data over the range of values, such as a bell-shaped. Data that have an approximately normal distribution are characterized by a frequency distribution with the following features. And these are the features of a normal distribution. Number one, the frequencies start low, then increase to one or two higher frequencies, and then decrease to a low frequency. And one of the problems we did look at that, and it did appear to have what they call a normal distribution. Okay. In fact, if I go back to example 3, this is where I was talking about the normal distribution. Starts low, reaches to a maximum number, then starts with a couple of low values here. Also, number 2, the distribution is approximately symmetric with frequencies preceding the maximum being roughly the mirror image of those that follow the maximum. Okay. So, in example 7, let's say you had this question. Does the frequency distribution appear to have a normal distribution using a strict interpretation of the relevant criteria? Okay. So here's that distribution. Take a look at those frequency values here. And if you look at it, you're going to see that it does not appear to have a normal distribution using those strict guidelines that I mentioned up here. So here we can say that no, that the distribution does not appear to be normal. Because notice here, for 40 to 44, that frequency is 0. Now, had that been taken out, then it may look like it might appear to be a normal distribution, but here you got the 0 in for that second class. So that's not going to be a normal distribution. Okay. Okay. Last thing I'm going to talk about in this video is just the gaps. Okay. Just like the one in that last example that I showed you. The presence of gaps can suggest that the data are from two or more different populations. However, the converse of this principle is not true because data from different populations do not necessarily result in gaps. Like in this example, the table below represents a frequency distribution of weights in grams of randomly selected pennies. Examination of the frequencies reveal a large gap between the lightest pennies and the heaviest pennies. This suggests that we have two different populations. Pennies made before 1983 are 95% copper and 5% zinc, but pennies made after 1983 are 2.5% copper and 97.5% zinc. Okay, so you can see that huge gap in between right here from 260 up to 2.60 up to 2.89. Okay, so this could be from two different populations. Okay. All right, that is all I have to mention here in this video. So that will conclude this entire video on section 2-2 dealing with frequency distributions. And hopefully this will be enough to assist you with the homework in that particular section.